welcome back to the tutorial video for multivariate analysis class. In this video, I will talk about the content of chapter 9 and the first part of chapter 10. Before getting into the details, you should first install two new libraries, the scheme-R library and the DMWR library. The scheme-R library, we will need the n unique function in it to calculate how many unique values are in a column, and in the DMWR function, we need the unscaled function to get the original value of a scaled column. Let's start from chapter 9. So chapter 9 is an introductory chapter for the more complicated models in future chapters. Previous chapters, we use Gaussian distribution and linear relationships to describe our model. However, the problems we have can't always be described this way. For example, if the outcome variable we want to estimate is the happening probability of a certain thing, it can be described by a Gaussian distribution, since the outcome values of probability can only be from 0 to 1. In this example, a binomial distribution may fit this kind of data better than a Gaussian distribution. In the following chapters, we will learn about how to apply these models into STEM. So for the binomial distribution example I just mentioned, if we want to estimate the probability in the binomial distribution, we can just use the linear relationship like alpha plus beta times x. Because the range of alpha plus beta times x is the whole real value, and which did not match the range for probability. If the ranges of the two values on the equal sign are different, we cannot get the correct estimation. So we need some transformations to make the ranges on the two sides of the equations be matched. And these transformations are called link functions. One very common link function to match real numbers and values in 0 to 1 is called logic function. If we put one probability p and into the logic function by p divided by 1 minus p, take the log, the output can be any real numbers. By doing so, we can use the linear relationship alpha plus beta times x to estimate the logic pi, and then use the inverse logic function to get the original p we want to estimate. Another very common distribution function we will use is Poisson distribution. And the parameter in a Poisson distribution is lambda, the average count. So an average count must be a positive real numbers, which also cannot be directly estimated using alpha plus beta times x. So the transformation function or link function we will use is a log function. So we will use alpha plus beta times x to estimate log lambda. In chapter 10, we will learn about these two kinds of counting regression model, binomial regression and Poisson regression. In the first part of chapter 10, we will learn about binomial regression. So we will use logic p equal to alpha plus beta times x as the regression function. But actually, there are two forms of the binomial regression. So the first form is when our n is equal to 1. So the output of y will be 0 or 1, and the parameter we want to estimate is p. And this kind of problem is called logistic regression, or we need to predict the outcome of the x values should be 0 or 1. The second kind of problem is when the n is larger than 1. So we need to know how many times in n times experiments will be successful result, and this is called aggregated binomial regression. And in this kind of problem, the outcome variable we want to predict will be the count of success. There are some difference in the STEM codes, and in some situations, these two kind of problems are interchangeable. So we will learn about the details here. Let's begin by learning logistic regression. The data we will use is the chimpanzee data. And there are 7 chimpanzees under 4 different treatments. So you can see the actor columns indicates which chimpanzees are in this experiment. And we have different situations like condition and prosocial left. These are the two controlled variables in our experiments. And the output variable is pull left. The chimpanzees in the experiment will pull the rings on the left or on the right. We would like to know the tendency for a chimpanzee to pull the ring on its left under different experiment situations. So I create a new column called treatment to store the experiment conditions for the chimpanzees. Treatment will be values from 1 to 4. Firstly, we have our base model where we only put the intercept term alpha in the regression equation. So the model is like kind of estimating the average probability for binomial, or we can say the average tendency for any chimpanzees to pull the rings on its left, regardless of the experiment conditions. The prior distribution of the intercept term alpha can still be a normal distribution. We can investigate which normal distribution is more reasonable in a logistic regression. Since the relationship between the predictors or the output variable in the GLM model is no longer linear, we can set the prior using just our intuition. We should visualize them to see if the priors are reasonable. So here I use two normal distribution, normal 0, 10 and normal 0, 1.5 to visualize the comparison. So in a simple linear regression, we may think a normal 0, 10 will be a very flat prior. However, this will not be the case in a logistic regression function. I use random normal function to draw 1000 samples from normal 0, 10 and normal 0, 1.5. So the output of normal 0, 10 will be something like this. You can see we have a very wide ranges of A1 values, and then I use the inverse logit value function to transform back these real numbers to probability. So the result of inverse logit A1 will be in the range of 0 to 1, you can see here. And then we can compare the density of normal 0, 10 and normal 0, 1.5 after inverse logit transformation. You can see that the output of the normal 0, 10 is actually very weird. Like most of the probabilities are centering around p equal to 0 or p. On the other hand, normal 0, 1.5 has a more uniform distributed prior distribution. Like we can have around equal probabilities in every values between 0 to 1. From the above experiment, we can tell that the prior we've set, such as normal 0, 10, may not be as flat as we expected after the transformation from any link function. So we have to be careful about our choice of prior in any GLM models. When using GLM models, it's very common that we have to do parameter transformations such as the logit transformation or log transformation. Just like I've mentioned in tutorial 0.4, we can declare these kind of transformed parameters into the transform parameters block to avoid declaring it too many times in different code blocks. So once I've declared the transform parameters in the transform parameters block, we can use the P here in the model code in the model part and the generated quantities block. The structure of the stem model is the same as simple linear regression. We need the sampling statement here, but now we replace the normal sampling statement to a binomial sampling statement. The pulled left is our y, and the value is either 0 or 1. And in the binomial sampling statement, there are two parameters, n and p. So n must be 1, since we have one row is one experiment. And in the generative block, also need to calculate the log likelihood for model comparison. And the only different thing is that we replace a log LPDF function with a binomial LPMF function. In the binomial LPMF function, we also need the y in our observation and the parameters we have in the sampling statement. So you can see that the output of the base model have alpha equal to 0.32 and the probability will be 0.58. So if you are not confident about the relationship between alpha and p, you can build in inverse logit transformation function and to see the results. It's again about 0.58. The second model, we add a treatment effect into the model by using index coding. So now we have different intercepts for different treatments. Should also do some experiments on different prior values for beta as well. Since we have more than one beta values, we are more interested in the differences between different treatments for different betas. Here, I compare the prior beta to be normal 0, 10 and normal 0, 0.5. You can see that if we set the prior distribution to normal 0, 10, the estimated difference between any two beta values will either be 0 or 1, which means one kind of treatment will result in no chimpanzees pulling left, and another treatment result in the chimpanzees always pull left. But this is not the result we like. So we be expecting that some treatments will increase some probabilities like 20% or 30% for chimpanzees to pull left, and another treatment will increase like 10 or 15% of the probability for chimpanzees to pull left. So the prior for normal 0, 0.5 is more realistic in this experiment. And then for the model code, we just need to modify the transform parameters block. Now we use a for loop to loop over all the observations and assign different p-values using the inverse logic beta, and with index coding, we can assign different beta values for different observation. And then we can see the result. You can see that we can have 4 different beta values, negative 0.09 to like 0.58. But you may wonder what this beta value really means in the original probability ranges. So you can use the inverse logic. So you can see that, okay, so for treatment 1, the resulting probability will be like 55%, and treatment 2, 65%. And you can see that the difference between treatment 1 and 2 is like 10%, and 1 and 3 is like 5%. So these results matched our original expectation. In the final model, we take the effect of different chimpanzees into consideration. So imagine if there is a left-handed chimpanzees, so under whatever treatments, each chimpanzee just like to pull the rings on its left. We want to take its kind of impact into consideration, make the effect of treatments clearer. So again, we use index coding for chimpanzee differences and treatment respectively. So you can see alpha is the effect for chimpanzee effect, and beta is the effect for treatments. And different alpha values will follow one normal distribution, while different beta effects will follow another normal distributions. I think this is the first time we have 2 categorical variables in our model, but the coding details are the same. So now we have, this is the original categorical variable in model 2. When we want to add another categorical variable, firstly we need to set how many levels are in this category and add the other predictors. And then for the parameters part, we can add the alpha parameters and with length A, and in the transform parameters part with an additional alpha parameter with actor index inside the for loop, and the rest of the model are the same. And then we can print the result like this. However, these values actually didn't tell us anything. So the author plot a very fancy posterior plot for us like this. So we have different actors, different chimpanzees from 1 to 7, and with different treatments and the proportion for these chimpanzees to pull left under different treatments. And there are even confidence interval predictions. So let me explain how to draw a plot like this. Let's analyze this plot first. So the first thing I notice is that there are 7 columns from actor 1 to actor 7 on this plot. Well, I directly think of the function facet rep. This is the first thing. And the second thing is that values are not count data. The y value is the proportion data. So we have to group our predictions by chimpanzees and treatments to convert the 0, 1 output to the proportion. Also, there are lines connecting different treatments and open circles and filled circles to separate different kind of treatments. So we all need to include this kind of information in our data frame for plotting. The first step is the same as what we did previously. So we extract the predicted P from our posterior prediction, and then use the apply function and HPDI function to calculate the confidence interval, the prediction mean, and then we add the original observations, actor, treatment, actual data in the data frame as well. And then we use group by and summarize to convert the 0, 1 output to proportion. For example, if we have 10 experiments in one pair of unique actor and treatment, among the 10 experiments, the chimpanzee pull the ring on its left for 5 times. So we take the mean and we can have the 50% proportion. We add 2 columns, food location and partner. So these columns will tell us what kind of conditions are in this treatment. So for treatment 1 and 3, the food is on the right-hand side. In 2 and 4, the food is on the left-hand side. And if the treatment is in 1 or 2, there's no partner, the opposite side of the chimpanzee. And if it's 3 and 4, there's a partner. Okay, so after these processes, we've got all the data we need to plot this plot. So firstly, we can plot the 2 lines here connecting vision. So here, the first 2 geometry are geometry line with one connecting foot on the right and one connecting foot on the left. And then we can draw the points with field open points and field points, geometric points, and then we need to add another aesthetic called field. Aesthetic is a partner. So with partner, it will be field, and without partner, it will be an open point. And notice that we have to add the shape equal to 21 because only shape 21 has the aesthetic field. And it's the prediction intervals for our posterior, and again we can use the geometric segment function like before y and yn values will be the lower and upper bound of our prediction intervals. And then we would like to have these horizontal dashed lines motion equal to 50%. So we can use the geometric horizontal line function, y-intercept equal to 0.5, and the line time is dashed. And then we can use the phase rep function to split our plot by to 7 columns by different chimpanzees. And do the same thing for observed data. So you can see we have 2 geometric line and 1 geometric point. So, and the result will be a plot on the textbook with a different order. So the first row of my plot is posterior prediction. You can see we have the annotation and the lines and the confidence and the prediction intervals and the different color of points, and the y values are the proportion, and we have 7 columns. It's posterior plotting, and we can just compare our 3 models. And from the result, you can see that the model actually expects no change when adding a partner predictor, so, and most of the variation in the prediction comes from the actor intercepts. In some situation, the aggregated binomial regression model is interchangeable with the logistic regression model. So for example, the chimpanzee data we used, if we aggregate the data by actor and treatment first, each combination of actor and treatment will has 18 experiments, and then our model now will be aggregated binomial distribution. So now, in this kind of situation, the output value y will be how many times the chimpanzee pull left during the 18 experiments. But the parameters we are going to estimate is still the probability p. And then here is our new data called D2 chimpanzees, and I create a new column, new pull left column, and it will be the sum of the pull left count after grouping by actor and treatment. So the result will be like this. Actor 1 under different treatments, we will have different counts of pull left under the 18 experiments. Chimpanzee 1, and in the second treatment, under the 18 experiments, the chimpanzee pull 9 times of the left rings. And then we can check our model. So we only need to modify the sampling statement from tilde binomial 1p to tilde binomial 18p, because now the n is 18. We also need to change the generated quantities block, the log-like values, and the prediction left, replace 1 with 18. And then we can compare the posterior prediction of the parameters of these 2 models, and we can see that coefficients are actually very similar. So for alpha 1, you can see 0.44 and 0.45, 3.9, 3.9. This comparison proves that these 2 models are interchangeable. You may also want to compare the WAIC value using the rethinking compare function. But and you will notice that wow, the aggregated binomial model have a much smaller WAIC value compared with the logistic regression model. However, this is not true because the aggregated model contains an extra factor in its log probabilities because the way of the data are organized. So in the aggregated form, it counts all the ways you could see n success in 18 trials. So basically, these 2 models have totally different likelihood function. So the WAIC value cannot be compared. And then we can see the second example of the aggregated binomial model. So in this case, we will use the UCB admit data. So in this data set, we can see there are a lot of applicants apply for different departments of UC Berkeley, and there are different admission rates for different departments. We want to know if there is a gender discrimination problem, the application process. So this is an aggregated binomial model with different n in different rows. So the n will be the applicants, where we have a y being the number of admitted students. So in the first model, we only take the gender effect into consideration. So okay, we can see the data part. As usual, we have a number of rows in the data n, and admit, which is our y, and number of levels in our categorical variable, and our gender effect. And this is another column, applicants, because we have different number of experiments or different number of n in different rows. And for the transform parameters block, we use the for loop to calculate an inverse logic function to calculate the p-value for each row. And then in the model part, just replace the 18 in our chimpanzee example with the column applications, and then use the p as usual. And in the second model, we not only consider gender effect, but also take department effect into consideration. So we have another variable called delta, with length 5, because there are 5 different departments in the example. We want to estimate the effect of each department. And for the model code, basically they're just the same. We just need to add the department columns, and in the parameters, we need one more parameters to estimate the delta. And in the transform parameters block, in the inverse logic function, we need to consider delta as well. And for the other part, they are just the same. Okay, there's actually one small thing in here in the generated quantities block. For the binomial RNG function, now we need to replace the 1 in chimpanzee example to applications I, because we would like to know how many admit counts will be drawn from n equal to the applications. So firstly, we print the result from the model with only gender effect, and we may conclude that male applicants enjoy a lot of advantage if we only look at the difference in the two alpha values. And we can see that if we use the inverse logic function to convert these alpha value to probability, we can see that female applicants have only 30% of admit rate, while male applicants enjoy like 15% more of the admit rate. Then if we consider not only the mean value from the summary report, but all the iterations in each chain of MCMC, you can see that difference are really at 15% of the admit rate. So can we conclude that male applicant really enjoy great advantage over female applicant? Well, the answer is no. If we borrow the code we use for chimpanzee dataset and plot our predictions against the real observation, these color points are our predictions for male and female admit rate, and the black lines and black points are the observed data. You can see that there are huge differences among different departments. That's why we also need to consider a department effect into our model. So we can see the posterior prediction from the second model with both gender and department. We can see the posterior summary report from the second model. You can see that the difference on the gender effect of the two alpha values are much smaller than that in the first model. But the department effect is huge. You can see that the department 1 will has a mean of 0.8, while department 6, the value is like negative 2.5. So you can see that the differences are larger than 3 in logic scale. If we plot the differences gender on the proportion scale, you can see that the differences of male and female is actually even smaller than 0.1. However, if we compare the differences between delta 1 and delta 6, you can see that the difference is around 60% of admit rate. And then we can plot the result on the same plot. Again, you can see the departmental effect is much higher than the gender effect. And this new model actually explain the observed data better than the model with only gender effect. We can have the two prediction plots together, and see, you can easily tell that the second model prediction is much closer to that of the first model. And then if we compare the WAIC value, the second model has a much slower WAIC value. So the second model tells us that the gender effect is actually not a key predictor. So this is not an evidence of gender inequality of college admission of UC Berkeley. This is the end of chapter 9 and the first part of chapter 10. And don't forget to check the tutorial video for the second part of chapter 10 to see more examples of counting and classification models.